Imitation learning trains an agent using a set of demonstrations. However, when this trained policy is executed, small action errors can lead to unseen states causing failure. Allowing a human to intervene during policy rollouts and provide corrections can mitigate these issues. However, prior methods have mainly been limited to 2D driving domains. This domain is very tolerant to error. The agent just has to stay on the road. However, 6-stop robot manipulation can have state regions that require high precision, such as insertion. These regions are much less tolerant to error, and a small deviation in a trained agent means the difference between success and failure. We call such regions bottlenecks. In this work, we address the problem of intervention-based learning for manipulation by building a system and an algorithm. Our system allows operators to remotely monitor train policies and intervene when necessary. An operator only requires a smartphone and a web browser. The operator watches the train policy in a video stream until they decide to intervene. When they intervene, they move their phone in free space to apply relative post commands to the robot arm. This provides a natural and simple way for humans to intervene and apply corrections. Our method partitions the non-intervention and intervention data into two datasets. The intervention portions usually start in bottleneck regions and show how to traverse the bottleneck. Capitalizing on this fact, we sample equally from the two datasets. This relates the data distribution to prioritize learning intervention behaviors, while the non-intervention samples regularize the policy. We call our method intervention-weighted regression, or IWR. This process of intervention data collection and training with IWR repeats. We evaluate our system and algorithm on two challenging multi-stage tasks. The first is threading, which contains two bottlenecks. The second is a coffee machine task where the robot needs to make coffee. The task has three bottlenecks. These tasks also require the robot to generalize to a large set of task instances. We collected data across three different operators. They differed in skill level and produced diverse quality data. The red borders denote user interventions. We compared using intervention-based learning with IWR to collecting an equivalent number of full human demos. The plots shows task success rate, and that IWR can consistently improve the base policy more than using full human demos. IWR also outperforms other intervention-based alternatives, like HG-Dagger. We also showed that IWR can learn from data collected by HG-Dagger, resulting in substantial gains, showing that the way intervention data is used in training matters substantially. These are some qualitative examples of interventions in the datasets. Notice that most interventions occur near bottlenecks. These videos show policies trained on the intervention data. There's clear evidence of corrective behaviors that are learned by the policies.